in that last video, why was I able to say, well, let's add up the whole electric field on one side of the boundary and equate it to the electric field on the other side of the boundary? Well, I found the total electric field on the left side. Total field on the right side is just that one term. It's just the transmitted. And it's got orthogonal parts in it. And whenever you have orthogonal parts, you really have separate equations. You can kind of slide them apart. So the tangential parts are always the ones that we care about matching up. So I had those in there. But I can separate them out and kind of write them as a different equation. Okay. And then I had to have phase continuity so that it would work at any value of x or y. We didn't really have any y propagation. All of propagation was in the xz plane, and of course z was fixed at 0 at any time. So with the phase continuity requirement, making all those exponential terms the same so we could divide them out, we got the frequency is the same everywhere. That's kind of reassuring. You don't want a different color light coming back out at you. That's what would happen. And the wave number is the same. All different components are the x and the y component, which we didn't have, are the same. Because we didn't learn anything about the z component because it got knocked out. So now we can draw these little pictures, just like we can break down the electric field into its tangential and normal components. I've taken these wave vectors. We know their magnitudes. I've taken them and tried to draw them along these directions. So this one is the incident wave vector, and its magnitude is k1. Okay, that's just set by the index of refraction in the material. Okay, and it's only material property here when you kind of bundle it up like that. What else do we have? These x components turned out to have to be the same across the boundary. So we've got the same, we'll just call them k sub x. We've got the same x height here, but different hypotenuse lengths. So we're in material 1 or material 2. Or material 1 or material 2. Okay, this one's different, and so I've got a different angle for the transmitted ray with respect to the z-axis. Got my incident angle, my reflected angle. You know where this is going. So we can write these things out as sines. So sine of the angle of incidence is going to be k sub x over k1. Sine of angle of reflection. Okay, that's got the same, we're just going to call those k sub x. Same little picture here, k sub x, and we're in material 1, so the hypotenuse up here is the same. So what we're learning here is angle of incidence is angle of reflection. They have the same sign. So theta I is theta r. So we kind of knew that a little bit already, and you're used to seeing that picture. And it comes back at the same angle. What's the other one? Well, now we have to deal with material 2 having a different index of refraction. Sine theta transmitted, same kx, but k2. Okay, so it's got a little bit longer one, the way I've drawn it here. Okay, we can put those things together. Sine. And what we really like is to have everything in terms of the angle of incidence, because we're in charge of that. We're aiming the laser pointer. Sine theta t over sine theta I. Okay, take this one, divide by this one, is k sub x over k2 divided by k sub x over k1. Get rid of those pesky k sub x's. And we're going to get k1 over k2. K1 over K2, and that's up here, omega n1 over the speed of light. That's the same in both of them. The speed of light vacuum is the same. It doesn't matter what material we're talking about. We're talking about approximately 3 times 10 to the 8th meters per second. Okay, same frequency, different index of refraction. Okay, and so we can eliminate a lot of things here. Doot. And we're getting back N1 sine theta incident is N2 sine theta transmitted. So this is Snell's laws of reflection and refraction. Just by matching up those boundary conditions. If you continue on with this, I'll be able to answer questions about it next week. Looking in chapter 10, we still didn't get much information about the amplitudes of the electric fields. We kind of said, well, these phases have got to be the same for this to work, so let's take that information and run with it. We've got some useful kind of guidelines for things we might have to do later on. We learned that the electric field is perpendicular to the propagation direction. Okay, kind of take apart Maxwell's equations and put some vector identities in there and get that property. Okay, so if we know these pieces of information about, well, we've got this incident angle, so we have to have these other angles right here, just because those phases have to match up. Now we can start matching the magnitudes of the electric field and the magnetic field and using those boundary conditions in a little more detail. And that's a little bit beyond our scope today, but it's in chapter 10.